All right, welcome to section 5.5. This section we're going to talk about exponential functions and investing. All right, so first in this section, we're really just going to go over a couple equations for figuring out a few different financial things here. So first one here is a future value of an investment with annual compounding. So compounding just means how many times they calculate in the interest that you earn. Okay, so this is the equation right here. All right, so just notice your parentheses, exponents, all that kind of stuff. Make sure you always follow PEMDAS. Always follow your order of operations. So in this case, you'll do what's inside the parentheses first, then you'll raise it to that exponent, then multiply by that p-value. Okay, all right. So you need to know what each of these variables mean, right? So P is the dollars that are invested. So in other words, it's the amount of money you put into the account. R is the interest rate per year, right? Compounded annually here. So the future value is S at the end of T years. Okay, so you're just going to read the problem and it'll say, with annual compounding, and it'll give you those variables. You plug them in, solve for the unknown. Okay, we'll do a few examples. Next one here is a future value of an investment with periodic compounding. In other words, not just once per year. So it could be different times, or different amount of times per year. So again, so this is the equation here. Again, make sure you always do PEMDAS. All right, so actually let's look at this one. So we will do what's inside the parentheses first, right? Make sure you multiply k times t, and then you'll take whatever this answer is and raise it to that power, okay? Then multiply by p. All right, that's really important. All right, so again, let's see. So p is the number of dollars invested, t is years, annual interest rate R in decimal form. Of course, these R's are always in decimal form. Interest is compounded k times per year. Okay, so if it says like semi-annual, that means twice a year. If it says quarterly, that means 4 times a year. Monthly would be 12 times a year. Daily, 365 times a year, etc. Then the interest rate per period, so R divided by K, is the number of compounding, or times the number of compounding periods, K times T. Okay? All right, so you're going to plug all that stuff in. So let's do a couple examples using those two equations. So A here, write the equation that gives the future value of $1,000 invested for T years at 8% compounded annually. So it says right there, compounded annually. So you're going to use this first equation here. All right, so this is what we're going to write. So write down the equation and then we'll plug what we know in. S equals P, parentheses, 1 plus R to the T power. All right, let's plug in what we know. Okay, so they said we're going to invest $1,000, so that's the P. 1 plus, so R is the rate in decimal form, so 8% is 0.08. To the T power, normally they're going to give you a value for how many years, but in this case they're saying write the equation. So we're going to use T right here. All right, and then we'll follow PEMDAS. The only thing we can do here is add right here inside the parentheses. So the final answer here is 1,000 times 1.08 to the T power. Okay. All right, now if they said, find the future value after 10 years, you would plug a 10 in for T and make your calculation. Okay. All right, next one here, part B, write the equation that gives the future value of the $1,000 invested for T years, 8%, now compounded daily. Okay, so this means we're going to use this second equation here because it's not once per year. All right, so S equals P times 1 plus R over K to the KT power. So of course KT means K times T. All right, we plug in what we know. Okay, so this is going to be, we're going to put $1,000 in. 1 plus 0.08 over, right, because R is the interest rate in decimal form, compounded daily, so K is 365 to the K times T power. So that's going to be to the 365 times T power. Okay, and there's our equation. You can plug this into a calculator and add it to 1 if you want. Okay. All right, so that's how you use these equations. Let's do a little bit more though. So part C says, what is the additional amount of interest earned in 30 years from compounding daily rather than annually? In other words, we're going to compare these two equations over 30 years and see the difference. So I'm going to change these, not going to change them really, but so I'm going to say this is future amount for part A and future amount for part B, just so we can distinguish between them in part C. Okay? All right, so in part A, all right, so part C, but we're going to do the future value of part A for 30 years. We said it's 1,000 times 1.08 to the 30th power. Okay, plug it into your calculator just as I wrote it there. It'll do the PEMDAS for you, but if not, make sure you do 1.08 to the 30th power first, hit enter, then multiply by 1,000. Okay, and if you do that, we should get, hopefully I made my calculations correct. Don't forget your dollar signs here. Should be $10,062.66. Okay. All right, so we'll hold on to that one here. Let's do the future amount for B. In other words, the daily interest, or the daily compounded interest. So that's 1,001 plus 0.08 over 365 times 365 times 30, right? 30 years. Okay. So if you punch that into your calculator correctly, again, watch PEMDAS, you should get $11,020.28. All right, but as always with word problems, what we want to do is we want to make sure we read the problem. All right, so it says, what is the additional amount of interest from compounding daily rather than annually? All right, so we're going to say, so to finally answer the question, we're going to say future amount from the daily, part B, minus the future amount from the annually. All right, so we'll do, 11,020.28 minus 10,062.66. And if you punch that into your calculator, it should be $957.62. Again, don't forget your dollar sign. Oh, and I forgot my dollar sign up here on part B. So there we go, $957.62 more from daily compounding. Oops, there we go. Okay, and there's your answer. So the more times they compound, the better. Okay, let's see. Next one, we have what's called continuous compounding. Okay, and it's just what it sounds like. It's always compounding. So if P dollars are invested for T years, so again, P dollars invested T years, annual interest rate R in decimal form, compounded continuously, then we use this equation right here. S equals P times E to the RT power. Okay, so same thing. We're just going to plug in what they give us and punch it into our calculators, right? All right, so it says, what's the future value of $3,500 invested? So S is future value. So we have 3,500 invested times E, 10 years at 9%. So that's 0.09 times 10 years. Okay, if you plug that into your calculator, you should get $8,608.61. Okay, so there we go. All right, and then part B says how much interest will be earned on this investment. So in other words, we're going to take the original amount. Well, actually, we're going to take the final amount minus the original amount, and that will give us our answers. So 8608.61 minus the original 3,500, and that will give us 5,108 and 61 cents. All right, so there you go. Over 10 years at 9% interest, compounded continuously, the interest, the extra amount of money you earn, is $5,108. Okay. All right. Next one here, we have what's called present value. So the lump sum that will give the future value S in n compounding periods at rate I per period is the present value. So I is the interest rate. Still, n is number of compounding periods, and S is the future value. Okay, so this is the way you'll see this type of problem presented. What lump sum must be invested at 10% compounded semi-annually? So semi-annually means 2 times a year. For the investment to grow to $15,000 in 7 years. So there we go, we plug everything in. So we want the present value that we need to put in. We want the future value to be 15,000. And we do 1 plus the interest rate is 10%, so be careful, that's 0.1 or 0.10, either way, for 7 years. Okay. Again, make sure you plug this in correctly into your calculator. Make sure you use these parentheses as I did here. If you punch all that in correctly, and assuming that I did as well, you'll get $7,697.37. All right, so that's how much money you have to put in for 10% compounded semi-annually for the investment to grow to $15,000 in 7 years. Okay. All right. So that's section 5.5. So we're on to 5.6. So 5.6, I'm only going to talk about the equations, and how to plug these in, or what each variable means. I'm not going to go through any examples, and there's not going to be any homework on 5.6. All right, so annuities and loan repayments. So here we go. Future value of an ordinary annuity. So if R dollars, so R is the amount that you contribute at the end of each period for n periods into an annuity that pays interest at rate I, then at the end of the period, the future value of the annuity is this equation in dollars. Okay, so a bunch of stuff to plug in, PEMDAS again, all that good stuff. Okay, we're going to go on to this one. This is present value of an ordinary annuity. So if a payment of R dollars is to be made at the end of each period, so again, R dollars per period, n periods, interest rate I, then the account is an ordinary annuity, and the present value is, again, this wild equation here. So you plug in PEMDAS, get your answer. All right, and I think just one more here. So amortization formula. So if a debt of $8, so that's how much you owe. So this is a good equation for paying off credit cards, mortgages, things like that, loans. With interest rate of I per period is amortized by n equal periodic payments made at the end of each period. Then the size of each payment is this equation here. And again, plug in, use PEMDAS, you got it. Okay? All right, and that's the last section of this chapter. Thank you very much.